So imagine you are packing your bags for the ultimate camping trip. Like, you've spent years prepping for this.
Right.
You've got all your highly specialized gear tested. You've, memorized the topographical maps of the trails. And you've told all your friends that you are finally going to be living entirely off the grid for a solid week.
Sounds like a pretty intense vacation.
I mean, in one of the most remote places imaginable, right?
Oh.
But then, right as you're zipping up your backpack and heading for the door, the trip planner just walks in and completely tears up the itinerary.
Oh, wow.
Yeah, they cancel your hotel reservations at the trailhead, look you dead in the eye, and say, change of plans. We aren't just camping anymore. We are building a permanent, self-sustaining settlement. And, you're leaving tomorrow.
It's the ultimate logistical bait and switch,
Yeah.
but operating on a multi-billion-dollar geopolitical scale.
Exactly.
And, it completely upends decades of established aerospace methodology.
Which is exactly our mission for this deep dive. We are going to unpack a massive, sudden, and frankly historic shakeup in space exploration that occurred in early 2026.
It really was an earthquake in the industry.
Yeah, because NASA hasn't just tweaked the edges of the Artemis program, right? They have completely rewritten the entire roadmap to the moon.
Right, from top to bottom.
We're talking canceled, multi-billion-dollar space stations, heavily repurposed nuclear reactors, the realities of extreme lunar survival, and a completely accelerated timeline that changes everything about how humanity operates in space.
I mean, it represents a profound philosophical and structural shift.
Mm.
We're essentially watching an agency pivot in real time from a model of temporary visitation to a model of permanent aggressive infrastructure.
To figure out how we got here and, well, where we are actually going, we have a really fascinating stack of sources for today's deep dive.
We've got a lot of ground to cover.
For sure. So we're looking at the recent, highly detailed Wikipedia updates on the Artemis III mission architecture.
Yep.
We also have a critical, deeply researched piece from the 21st Century Tech blog that kind of dissects the financial and political fallout of this shift.
Which is a really interesting perspective.
And we are digging right into the raw source material with NASA's official Moon Base User's Guide and a joint press release hot off the presses from NASA and the Department of Energy.
Right, and the through line of all these documents tells a very clear story of cause and effect. To understand the new plan, we first have to understand the immediate stumbles of the original plan.
Like, specifically, what went wrong with Artemis III?
Exactly.
Yeah.
From there, we can look at the administrative earthquake that led to the shocking cancellation of the Lunar Gateway Station.
Which was huge.
Massive. And that directly birthed the ambitious new ignition project. Once we map out that new timeline, we really have to look at the brutal, unyielding environmental physics of the lunar South Pole.
Because it's not a friendly place.
No, not at all. And finally, we'll look at the nuclear energy solution that makes this entirely new vision possible while pointing us straight toward Mars.
Okay, let's unpack this. Before we can even conceptualize building a sprawling city on the moon, we have to look at the immediate next step to get there.
Or rather, the step that was supposed to get us there.
Right. Artemis III has historically been the, emotional and operational anchor of NASA's modern return to the moon.
It was the crown jewel. I mean, the original plan for Artemis III, since the program's inception, was monumental in its scope.
Yeah.
It was slated to be the first crewed lunar landing since Apollo 17, way back in 1972. The goal was straightforward, but incredibly complex.
So 2 astronauts on the lunar South Pole for a surface stay of about 1 week.
Exactly. The total mission duration, factoring in the transit to the moon and the journey back, was going to be around 30 days.
And for a long time, that was the dream everyone was working toward. But the 2026 reality hit the aerospace industry hard, didn't it?
It was a very harsh reality check.
In February of 2026, NASA announced a massive pivot. Artemis III is no longer a landing mission. It is now slated for mid-2027, and instead of touching the lunar surface, it is going to be an Earth orbit rendezvous and docking test. The actual landing, the historic boot prints in the dust, has been pushed to Artemis IV.
Which is tentatively scheduled for 2028. From a public relations standpoint, it was a bitter pill to swallow for space enthusiasts.
Oh, absolutely.
But when you dive into the engineering reality, this delay was practically inevitable. There are 2 primary drivers behind this massive shift in the architecture.
Okay, what's the first one?
First, and arguably most critical, NASA has been grappling with serious lingering concerns regarding the Orion spacecraft's heat shield.
I want to dig into that for a second, because we throw the term heat shield around like it's a windshield on a car. But the physics of returning from the moon are terrifying.
Terrifying is a good word for it.
When you are re-entering Earth's atmosphere at lunar return velocities, you are hitting the thin air at roughly 25,000 miles per hour, right?
Yeah, the friction creates a plasma sheath around the capsule that is thousands of degrees hot.
Literally hotter than the surface of some stars.
Precisely. And the heat shield is an ablative material. It is designed to slowly burn away in a highly controlled manner to dissipate that immense thermal energy.
So it's supposed to get destroyed just in the right way.
Right. But if the data from previous uncrewed flight tests showed irregular wear patterns or unexpected cracking in that ablative material, you stop the presses.
You simply do not gamble with the fluid dynamics of a 5,000-degree plasma field when you have a crew inside.
Exactly. You have to understand exactly why the material's behaving the way it is before you clear it for a lunar return.
Okay, so heat shield issues are driver number one. And the second driver for the delay.
The landing system itself. There have been significant compounding delays in the development of the Human Landing System, or HLS.
Right, the SpaceX vehicle.
Specifically, yeah, the architecture relied on SpaceX's Starship HLS, which was supposed to be the vehicle ferrying astronauts from lunar orbit down to the surface and back up again.
Which makes sense when you look at the scale of Starship. I mean, it isn't a small, fragile Apollo lander. It's practically a skyscraper.
It's massive.
Trying to land a skyscraper on an unprepared, uneven lunar surface while dealing with cryogenic fuel transfers in deep space just to get the lander to the moon in the first place, I mean, that is a staggering developmental hurdle.
It is an unprecedented engineering challenge.
Yeah.
And because those two critical paths, the heat shield for the return and the Starship for the landing, were not maturing fast enough, NASA had to rethink what they could realistically accomplish.
With the hardware they currently had ready.
Right.
Let's talk about that hardware, because even with the mission profile shifting to a docking test, the sheer mechanical reality of what is sitting in the vehicle assembly building is incredible.
A marvel.
For Artemis III, they are using the Space Launch System, the SLS, which is NASA's super heavy lift rocket. And what blows my mind is how they are sourcing the engines for the core stage.
Yeah, this is a great detail.
They are actually using refurbished space shuttle engines. We are taking the exact engines that flew dozens of times in low Earth orbit in the 1990s.
Yep.
I mean, specifically, engines E-2048, E-2052, E-2054, and E-2057, we are completely rebuilding them and strapping them to the bottom of a rocket designed to hurl humanity back into deep space.
It is a fascinating approach to hardware procurement. It's a brilliant recycling of proven technology, but it also highlights the immense physical stress involved.
Because SLS is way more powerful.
Right. The SLS operates at a significantly higher performance level than the Space Shuttle did. Those legacy engines are being pushed to operate at 109% of their original rated power level just to get this massive stack off the pad.
Wow. And the spacecraft sitting on top of that rocket is an equally impressive feat of international collaboration.
It really is.
You have the European Service Module, the ESM-3, delivered by Airbus in Germany, which acts as the powerhouse. It provides all the propulsion, the solar power, and the critical life support consumables.
And that is mated directly to the Orion pressure vessel itself, the actual crew cabin built down in New Orleans by Lockheed Martin.
But because of this 2026 pivot, all of this highly specialized hardware is now the subject of a fierce debate among mission planners, right?
That's right.
If they aren't going to the moon on Artemis III, and they are just doing a rendezvous and docking test, where exactly in space are they doing it?
That is the crux of the current operational debate. The mission planners have to decide between two very different trajectories.
Okay.
They're looking at either a low Earth orbit profile or a high Earth orbit profile. And both have incredibly compelling arguments.
Well, I would assume low Earth orbit makes the most sense if you are just testing docking mechanisms. It's closer to home.
That's true.
The communication delays are practically non-existent, and if something goes wrong, the abort scenarios to get the crew home are much faster.
That is the safety argument, for sure. But there is a massive logistical argument for low Earth orbit as well.
Like saving hardware.
Exactly. If they stay in LEO, they don't need to fire the rocket's upper stage, the interim cryogenic propulsion stage, or ICPS, to push them out toward the moon.
Oh, right.
And NASA only has one of those specific ICPS upper stages left in their inventory. So if they run the mission in low Earth orbit, they can actually save that multi-million-dollar piece of hardware and reallocate it for Artemis IV.
Okay, saving an entire propulsion stage is a huge economic win. But on the flip side, what is the argument for pushing the mission out into high Earth orbit?
The argument is about testing the hardware in the environment it was actually built for.
Right, putting it through its paces.
Yeah, if you push the Orion capsule out into high Earth orbit, you are stepping out of the protective thermal cradle of Earth's immediate environment. You are exposing the spacecraft to deep space radiation, wild temperature fluctuations, and operational isolation.
So it's much more brutal.
Very. A high Earth orbit profile provides a far more rigorous, punishing test of Orion's life support systems. And crucially, it allows for a much faster re-entry velocity.
Oh, to truly test that heat shield we were talking about earlier before they commit to a lunar return on Artemis the 4th.
Exactly.
Hold on, I'm trying to connect the dots here, and I'm hitting a massive contradiction.
Okay, what is it?
We are sitting here debating whether to test a spacecraft close to Earth or far from Earth because we are struggling with heat shields and landing systems just to manage a single one-week visit to the moon.
Right.
If Artemis III is stumbling just to confidently get a capsule to orbit and back, how can we possibly be talking about building a permanent lunar city by 2030? If the basic transportation is this delayed, isn't a permanent base a total pipe dream?
Well, you have just articulated the exact realization that triggered an administrative earthquake within NASA.
Because the math just wasn't adding up.
Exactly. The delays and the technological bottlenecks of Artemis III forced a massive, agency-wide recalculation. The old way of doing things, slow, incremental steps, spreading development out across vast, slow-moving international bureaucracies, was simply not yielding results fast enough.
It wasn't meeting the geopolitical goals of the program.
Right. The timeline was slipping, and the costs were ballooning.
Which means someone had to come in and shake the tree. And that brings us to the new boss. Let's talk about Jared Isaacman, who took over as NASA administrator in 2026.
He was a very disruptive figure.
Yeah, this is a fascinating choice for leadership because he is not your typical lifelong government bureaucrat who came up through the ranks of the civil service.
No, not at all.
He is a billionaire astronaut. He commanded and entirely privately funded 2 SpaceX missions, one in 2021 and another in 2024.
Right. His entire operational background is rooted in the commercial space sector.
Which is a totally different culture.
Absolutely. He comes from a world of moving fast, taking calculated risks, leveraging private capital, and iterating rapidly on hardware.
Reading about his early moves as administrator, it feels exactly like a tech startup CEO taking over a massive, century-old legacy corporation.
It really does.
He walks in, looks at this sprawling, complex organizational chart of international dependencies, and just starts cutting the fat to force momentum. He basically decided that if the goal is to build a base on the moon, then anything that is not directly putting hardware on the lunar surface is a distraction.
And his first major cut was an absolute bombshell.
It really was.
It sent shockwaves through the global aerospace community. As heavily detailed in the 21st Century Tech blog source, on March 24, 2026, Isaac Dugnan announced a stunning $20 billion change in plans.
Which is just a mind-boggling number.
And the headline of that massive restructuring was the immediate, unceremonious cancellation of the Lunar Gateway.
The Gateway, I mean, this wasn't just some fringe concept. This was supposed to be a state-of-the-art space station in permanent orbit around the moon.
Yeah, a major piece of infrastructure.
It was meant to be the way station, the orbital staging ground, where astronauts would arrive from Earth, live for a bit, and then transfer to the landers. And it was a $5.3 billion project with actual hardware already bending metal on factory floors.
Which is why the global supply chain fallout from this cancellation was so staggering.
Oh, I bet.
The Gateway was the cornerstone of NASA's international coalition. Contracts were deeply underway across the planet. By axing it, Isaacman essentially severed immediate orbital contracts with nearly all of their major international partners.
Because everyone had a specific module they were responsible for, right?
Exactly. The European Space Agency and Thales Alenia Space were deep into building the sophisticated communications links for the HALO module.
And Japan was involved, too.
Right. The Japan Aerospace Exploration Agency, JAXA, was tasked with building the critical life support and thermal control systems for the primary crew module, known as 1HAB.
I remember seeing the mock-ups for the robotic systems, too. Canada was heavily invested in that, right?
They were. The Canadian Space Agency, along with MDA Space, was developing Canadarm3.
Which was more than just a crane.
Oh, way more. This was a next-generation robotic arm incorporating highly advanced artificial intelligence designed to maintain the station autonomously when crews weren't present. Even the Mohammed bin Rashid Space Center in the United Arab Emirates was in the process of building the Emirates airlock. By killing the Gateway, Isaacman told all of these space agencies and massive commercial prime contractors to just stop what they were doing.
Now, when you read the tech blog's analysis of this, it becomes clear that this wasn't just a rogue CEO making a unilateral financial cut out of nowhere.
Right, there's a policy framework behind it.
Exactly. The blog points out that this aggressive restructuring is heavily tied to the administration's stated America First space policy.
Yes.
Now, we are just conveying the policy context provided in the source material here, but the framework driving this timeline focuses heavily on utilizing domestic commercial partners to achieve, quote, American space superiority.
That was the stated goal, yes.
The reasoning given in the documents is that relying on complex international coalitions to build a space station piece by piece simply slows down the timeline too much. So the pivot favors forging new, rapid domestic partnerships, like teaming up with the Department of Energy to get hardware directly to the moon as fast as possible.
And while that rapid domestic pivot caused immense friction internationally, what's fascinating here is that the engineering concepts behind the Gateway might not be dead forever.
Oh, really?
Yeah, the tech blog makes a very astute point about the long-term utility of lunar orbit infrastructure. They suggest that a gateway-like structure could eventually be revived later in the 2030s.
But not as a mandatory stop for landings.
Right, not as a toll booth that slows down lunar landings, but as something incredibly useful. It could be a cislunar gas station for refueling deep space probes, a high-resolution Earth observation platform, or even an early warning detection system for space rocks threatening Earth.
Okay, so the orbital station concept has merit, but Isaacman's administration determined it was an operational bottleneck that was slowing down the immediate mandate of putting boots and permanent habitats in the lunar dirt.
Precisely.
So if the Gateway is dead, NASA didn't just pocket that $5.3 billion, dust off their hands and go home.
No, they reallocated everything.
They took all those funds and all those frustrated international partners who suddenly had no modules to build and redirected them toward a much more aggressive direct-to-surface strategy.
They removed the orbital middleman. The new plan is direct insertion to the lunar South Pole.
Which brings us to the core of this entire massive pivot, Project Ignition.
This is the big one.
This is NASA's new, hyper-accelerated plan to establish a permanent, continuously occupied lunar base near the South Pole by 2030. Let that sink in for a second. 2030.
It's aggressive.
That is less than 4 years away from the timeline in our sources. That is practically tomorrow in aerospace manufacturing terms.
To achieve something that monumental on that kind of timeline, NASA couldn't use the old Apollo playbook.
Right.
The Moon Base User's Guide outlines a highly structured, remarkably aggressive, three-phase iterative approach. It's all about building up capability rapidly, step by step, anticipating failures, and iterating on the fly, rather than trying to launch an entire perfect city all at once.
I want to break down these phases because when you look at the raw numbers, the scale is genuinely hard to wrap your head around. Phase 1 is officially called Build, Test, Learn.
And Phase 1 is essentially the robotic vanguard. It relies heavily on the Commercial Lunar Payload Services Program, or CLPS.
Okay.
This phase is about establishing ground truth data and proving high-rate, reliable access to the lunar surface. The sheer cadence of Phase 1 is intense. They are projecting 25 launches, resulting in 21 successful landings.
Wait, let's do the math on that. 25 launches to get 21 landings means they are openly forecasting a nearly 20% failure rate.
Yeah, they are.
They are expecting 4 of these rockets to crash or fail in transit. That implies they are treating these initial launches as almost expendable trial and error runs.
Which is a very commercial sector mindset. Space is hard, and the lunar South Pole is incredibly unforgiving.
Right.
Instead of spending 10 years and $10 billion to ensure one single rover lands perfectly, you spend less money buying 25 commercial landers and accept that some will crash while you dial in the navigation algorithms.
That is a huge shift in philosophy.
It is. Through those 21 successful landings, they plan to drop roughly 4,000 kilograms of payload to the surface.
But this isn't crude hardware yet, right?
No. These are small-scale technology demonstrations, robotic scouts, and site preparation tools. They are sending autonomous bulldozers to level the landing pads before the humans arrive.
Wow. Okay, so once the ground is prepped, we hit Phase 2, establish early infrastructure. And the escalation here isn't just a step up, it is a massive, unprecedented leap in logistics.
It truly is. Phase 2 projects 27 launches and 24 successful landings.
Okay.
But look at the payload mass. It jumps from 4,000 kilograms in Phase 1 to 60,000 kilograms in Phase 2.
That is a 15-fold increase in mass delivered to another celestial body. I mean, how do you even manage that?
You bring in the super heavy lift commercial vehicles like Starship and Blue Moon. This is where human beings finally enter the permanent architecture.
Okay, here we go.
Phase 2 features a first crewed moon base mission. And crucially, this is where the international partners who lost out on the Gateway are brought back into the fold.
Ah, so they aren't left out after all.
Exactly. For instance, this phase will utilize JAXA's pressurized lunar terrain vehicle. So Japan is still deeply involved in human exploration, just driving on the surface instead of providing life support in orbit.
That makes sense.
This phase establishes semi-annual crewed missions, meaning teams of astronauts are visiting twice a year, living in this early infrastructure while they deploy power grids and expand the footprint.
Which sets the stage for the endgame. Phase 3. Enable long-duration human presence.
Phase 3 is the full realization of the Project Ignition dream. The cadence here is staggering. 29 launches, 28 successful landings.
And the mass.
An astounding 150,000 kilograms of payload delivered and integrated on the lunar surface.
For context, because 150,000 kilograms is just a massive abstract number, the entire International Space Station, which took 15 years and over 30 space shuttle flights to build in zero gravity, weighs about 420,000 kilograms.
Right.
NASA is planning to drop more than a third of an ISS onto the surface of the moon in just this single phase.
And that mass allows for continuous crew presence. The paradigm completely shifts.
You aren't just visiting the moon anymore.
No, the base is permanently occupied, rotating crews in and out, just like a research station in Antarctica. In this phase, we see the integration of the Italian Space Agency's multi-purpose habitats and the Canadian Space Agency's lunar utility vehicle for heavy hauling.
So the whole gang is back together.
Yeah, the entire international coalition from the canceled Gateway has been successfully transplanted and integrated into a sprawling surface architecture.
What fascinates me about this three-phase plan is the underlying business model. NASA isn't building these landers in-house.
No, they're buying services.
Right. They are explicitly using bulk buys and multiple commercial contract awards. They are deliberately trying to create an economy of scale.
Which is key.
By guaranteeing commercial companies that NASA will buy 20 or 30 launches over a few short years, they give those companies the financial security to invest in massive production lines. NASA isn't just building a base, they're trying to spark a true self-sustaining commercial lunar marketplace.
It's the difference between custom building a single beautiful bespoke carriage in a workshop versus Henry Ford building an assembly line.
Exactly.
NASA wants the assembly line. They want landers rolling off the factory floor like pickup trucks because that is the only way to sustain a 150 metric ton logistical chain.
Okay, so on paper, an assembly line three-phase plan looks fantastic, but it is one thing to draw up an itinerary in an air-conditioned boardroom in Washington, D.C., and it is entirely another to actually execute it in one of the most brutal, hostile environments in the solar system.
It's an incredibly harsh reality down there.
Why is the lunar South Pole so incredibly difficult to operate in?
Well, the South Pole was chosen for one singular, incredibly valuable reason: water. Deep inside the permanently shadowed craters of the South Pole, there are vast deposits of frozen volatiles, primarily water ice. Water is the undisputed oil of the 21st century space economy.
Because it's so heavy to bring from Earth.
Right. You can purify it to drink, you can use it to grow plants in a habitat, and crucially, through electrolysis, you can split that water into hydrogen and oxygen to manufacture rocket fuel right there on the moon.
But the geography you have to navigate to get to that water, it is an environment of absolute extreme.
Unforgiving is an understatement.
If you want a relatable analogy, imagine trying to drive a heavy, delicate delivery truck through a canyon. But the canyon is pitch black. The walls are impossibly steep. The ground is hundreds of degrees below zero.
This is fun.
And the road is completely covered in massive, invisible potholes that could swallow your truck whole. That is navigating the terrain of the South Pole.
And even if you can navigate the terrain, the NASA architecture documents highlight the lighting problem as the primary environmental hurdle.
Why is the lighting such a big deal?
Because of the moon's axial tilt at the South Pole, the sun doesn't rise high in the sky like it does at the equator. It stays incredibly low on the horizon, practically skimming the surface of the landscape.
Which means any terrain feature, even a small hill, casts a massive shadow.
Dramatic, kilometer-long shadows that stretch across the craters.
Yeah.
And on the moon, with no atmosphere to scatter light or hold heat, if you step behind a boulder into one of those shadows, you aren't just standing in shade.
You're in trouble.
You are plunged into absolute darkness and immediate cryogenic cold. This lighting environment completely kills traditional solar power generation.
Because the shadows move.
Right. If your solar panels happen to be shadowed by a crater rim for a few days, your base dies. Furthermore, the rotation of the moon means that the lunar night at the pole can result in up to 120+ hours of continuous freezing darkness.
And my first thought was, well, just bring big batteries to charge during the sunlit days.
A lot of people think that.
But when you think about the mass constraints we just talked about, batteries alone are simply too heavy to launch. You cannot physically carry enough chemical batteries to power a habitat's life support, heaters, and water recycling systems through 120 hours of darkness.
Which brings us to what NASA meticulously details in their user's guide as the functional gaps.
The things we don't know how to do yet?
Exactly. These are the specific operational capabilities that we literally do not possess right now, and that we must absolutely figure out in Phase 1 if Phase 2 and 3 are going to happen.
Let's run through the critical ones, because they read like a sci-fi survival checklist.
Okay, let's do it.
First is robotics. We need robotic systems capable of autonomously unloading hundreds of kilograms of cargo from a lander and precisely mating electrical cables together in a vacuum.
That's a huge hurdle.
You can't just have an astronaut in a pressurized, bulky suit trying to bend over and plug in a massive extension cord every time a cargo ship lands. The dexterity just isn't there, and the risk of tearing a glove is too high.
Exactly. And closely tied to that is the gap in logistics. How do you transfer pressurized water and cryogenic liquid gases between a storage tank on a lander and a habitat module on the moon?
Right, because fluids act weird in space.
Very weird. You're dealing with extreme temperature differentials in a vacuum. A valve that works perfectly on Earth can cold weld itself shut in space, or a rubber seal can freeze and shatter like glass when the cryogenic fuel hits it. We have never done large-scale automated fluid transfer on the lunar surface.
Then there is the deeply unglamorous gap of habitation, specifically waste management. When Apollo astronauts went to the moon for 3 days, they used incredibly rudimentary systems, essentially bags. But if you have a crew of 4 staying in a habitat for 6 months, you have to manage human waste, food packaging, and biological byproducts continuously.
It's a massive sanitation issue.
You have to compact it, stabilize it, and store it without contaminating the highly sensitive scientific environment outside the airlock. Not to mention, you need medical countermeasures to stop their bones and muscles from degrading during long-duration stays in 1/6 gravity.
And you cannot manage any of this without solving the communications gap. The South Pole is on the edge of the moon, as seen from Earth. It does not have a direct, continuous line of sight to our planet.
Oh, because the Earth dips below the horizon.
Right. To get the required data rates to run a modern autonomous base, which NASA states requires greater than 500 megabits per second for video feeds, telemetry, and robotic control, they desperately need to build a second orbital relay constellation.
Like lunar internet.
Pretty much. They have to launch a network of satellites orbiting the moon just to bounce signals from the South Pole over the horizon and back to Earth.
But of all the environmental challenges, of all the gaps in our technology, the one that seems the most aggressively hostile, the one that threatens literally every piece of machinery they send, is the dust.
Ugh. Lunar regolith. It is the absolute bane of lunar exploration.
Because it's not like Earth dust, right?
The crucial thing to understand is that lunar dust is absolutely nothing like dust on Earth. On Earth, a grain of sand or dust is constantly weathered by wind and water over millions of years.
So the edges are smoothed down, it becomes rounded and soft.
Exactly. But the moon has no atmosphere, no wind, no water. Every single microscopic particle of dust on the lunar surface has been created by micrometeorites smashing into the rock for billions of years. It is not sand. It is essentially microscopic, jagged shards of broken glass.
Wait, and with no atmosphere to protect the surface, the moon is just constantly bombarded by solar radiation, right? Doesn't that mean the dust is essentially holding a massive static charge?
That is the nightmare scenario for electronics. It is highly electrostatic. Because it is constantly irradiated, the dust acts like a balloon rubbed on a sweater, but on a lethal scale. It clings to absolutely everything it touches. During the Apollo missions, it got into the threads of the spacesuit joints and ground them down until they barely moved. That sounds dangerous.
It coats thermal radiators, causing equipment to overheat. It threatens pressurized mating systems. If that abrasive, glass-like dust gets inside the rubber seal of a habitat's airlock, Every time you open and close the door, you are slowly carving away the integrity of the pressure vessel holding your atmosphere in.
And as bad as the dust is just sitting there, the architecture documents reveal that our massive commercial landers are about to make the dust problem exponentially worse through a phenomenon called plume surface interaction.
Plume surface interaction, or PSI, is a terrifying physics problem that scales up directly with the size of your rocket.
Right.
When a massive Phase 2 or Phase 3 cargo ship, we're talking heavy landers like Starship delivering tens of thousands of kilograms, fires its descent engines to land, the exhaust interacts with the lunar surface.
And in a vacuum, that's bad.
On Earth, when a rocket launches, the exhaust billows into huge clouds because it is pushing against the atmospheric pressure. In a vacuum, there is no air pressure pushing back, so the exhaust doesn't billow, it just expands instantly outward. It essentially turns the lander's engine into a giant hypervelocity shotgun.
That is the exact mechanism. The rocket exhaust blasts those microscopic glass shards outward horizontally at supersonic speeds.
Wow.
If you land a massive supply ship too close to your newly built habitat, the plume surface interaction could literally sandblast your delicate solar panels to pieces, pit the structural integrity of your habitat windows, or completely destroy millions of dollars of nearby scientific equipment.
So how do you stop that?
To solve this, before the heavy landers arrive, we have to figure out how to use small robots to melt the lunar dirt into blast shields or build hardened landing pads miles away from the base.
Okay, let's look at the totality of this nightmare. We have abrasive, clinging glass dust that destroys seals. We have plume surface interactions turning rockets into sandblasters.
Yep.
We have deep craters blocking the sun. We have up to 120-hour nights of cryogenic freezing. If solar power is incredibly fragile and unreliable in the dark, and chemical batteries are too heavy to launch, how on Earth, or rather, how on the moon, do we generate enough energy to keep the astronauts alive?
That energy deficit forced NASA to look at a completely different paradigm. The answer lies in a brand new partnership that changes the entire foundation of space infrastructure.
In January of 2026, NASA and the Department of Energy signed a landmark Memorandum of Understanding.
Which was a huge pivot.
Their joint goal: to bypass solar entirely and deploy a fully autonomous fission surface power system on the moon by 2030.
And if we look back at the administrative shakeup we discussed earlier, there is a brilliant piece of engineering sleight of hand that happened here.
Oh, with the gateway?
Exactly. The canceled Lunar Gateway originally included a highly advanced electric propulsion element. It was the small nuclear reactor designed to power the station's ion thrusters and move it around cislunar space. That reactor was designated Space Reactor 1, or SR-1 Freedom.
So when Administrator Isaacman killed the Gateway Station, he didn't kill the reactor, he just brought it down to the surface.
It is a masterpiece of repurposing hardware. SR-1 Freedom is now the beating heart of Project Ignition. And the engineering why is undeniable.
Because it solves the night problem.
Yes. A fission surface power system completely neutralizes the 120-hour night problem. It provides continuous, abundant, and incredibly reliable electrical power. They are targeting at least 5 kilowatts of generation and storage.
That's amazing.
And it does this regardless of the cryogenic temperature, regardless of whether it's hidden in the shadow of a crater, and regardless of how much abrasive dust coats its exterior.
5 kilowatts might not sound like a massive power plant to run an entire base. I mean, a typical Earth home uses a few kilowatts.
Right, it's not a lot on Earth.
But in the hyper-efficient world of space survival, it is enough to keep the critical life support cycling, the communication arrays broadcasting, and most importantly, the thermal heaters running during those brutal 2-week-long lunar nights so the water pipes don't freeze and burst.
It's life or death power.
U.S. Secretary of Energy Chris Wright had a massive quote in the press release about this joint venture. He compared this technological leap to the Manhattan Project and the original Apollo missions combined. He called it, quote, one of the greatest technical achievements in the history of nuclear energy and space exploration.
While it sounds like political hyperbole, from an engineering standpoint, he isn't exaggerating. Putting a safely functioning nuclear reactor on another celestial body requires solving incredible physics problems.
Because you can't cool it normally.
Right, you have to manage thermodynamics in a vacuum. On Earth, nuclear reactors are cooled by massive towers of water or air, In a vacuum, you have no medium to dump your excess heat into.
So what do you do?
You have to design highly exotic liquid metal cooling loops and massive thermal radiators. You have to design lightweight radiation shielding so you don't cook the crew living half a mile away.
And it has to turn itself on.
Yes. You have to design it for fully automated deployment. Remember, you can't exactly have astronauts standing next to the core with wrenches, making adjustments when it first powers on.
It is the ultimate off-grid survival tool. But here is where the entire narrative of our deep dive converges into something even bigger.
The big picture.
Exactly. Everything we've talked about so far. The shift to massive commercial launch contracts, the autonomous site prep robotics, the mitigation of electrostatic dust, the repurposing of a nuclear reactor. None of this is actually just about the moon.
No. The moon is simply the proving ground. It is the sandbox. The true target, the actual reason for the aggressive timeline of Project Ignition, is Mars.
Every single piece of technology designed to survive the lunar South Pole is a calculated dress rehearsal for the red planet.
Let's start with the energy paradigm. Why is NASA so adamant about pushing through the immense regulatory and technical hurdles of using nuclear fission on the moon?
Because of Mars.
Because they have already concluded that nuclear fission is the only viable primary power choice for a human mission to Mars.
But Mars has a day-night cycle very similar to Earth, right? Like a roughly 24-hour day, the sun rises every morning. So why not just use vast fields of lightweight solar panels there?
Because Mars has an atmosphere. It's thin, but it is enough to create dynamic weather systems.
And weather means storms.
Exactly. And that weather creates global, planet-wide dust storms that can last for months at a time, completely blotting out the sun. We have lost multiple multi-million-dollar robotic rovers, most notably the Opportunity rover, because Martian dust permanently coated their solar panels during a storm and starved them of power.
So solar is too risky for humans.
You cannot stake human lives on solar power when the sky might turn dark for 3 months. A nuclear fission reactor is completely robust against Martian dust storms. If you prove that SR-1 Freedom works flawlessly for 5 years in the dust and cold of the moon, you have the confidence to know it will keep your astronauts alive during a global blackout on Mars.
And the shared engineering goes so much deeper than just power. The NASA User's Guide explicitly lists the overlapping operational benefits.
Oh yeah, operations are huge.
By building this moon base, they are rigorously testing what they call Earth-independent operations. If communications go down or a life support pump fails, the astronauts need the tools, the 3D printers, and the autonomy to diagnose and fix the base entirely by themselves.
They have to be self-sufficient.
You can safely test that operational psychology on the moon, which is only a 3-day emergency flight back home, before you test it on Mars, which is a minimum 8-month journey away.
Testing those operations also brings up a vital, rigorous scientific discipline called planetary protection.
I saw this detailed in the interagency documents. It sounds like something out of a Michael Crichton sci-fi novel, but it is a massive driver of how they design the airlocks and the habitats.
It is a very real, incredibly strict framework governed by international treaty. Planetary protection essentially has 2 branches that must be managed.
Forward and backward, right?
Yes. Forward contamination is the incredibly difficult task of preventing Earth microbes, bacteria, fungi, extremophiles from hitching a ride on our spacecraft, our spacesuits, or in our waste venting, and contaminating the Martian ecosystem.
Because that would ruin the science.
If we are spending billions to search for native indigenous life on Mars, we cannot accidentally seed it with life from Earth and ruin the scientific baseline.
And backward contamination is the reverse. It is preventing whatever microscopic life might theoretically be living in the Martian soil from coming back to Earth on a returning spacecraft and interacting with our biosphere.
That's the scarier one.
So developing the strict protocols for how an airlock cycles, how a suit is sterilized with UV light or chemical baths before it enters the habitat, and how geological samples are handled in a vacuum glove box at the moon base. All of that is the mandatory prerequisite for safely managing planetary protection on Mars. The Mars connection gets even more tangible, almost visceral, in the final pages of the architecture documents. There is a fascinating detail tucked into the NASA executive summary that shows exactly where their heads are at.
The helicopters.
Yes. The overall mission architecture for the 2030s now officially includes the development of a fleet of robotic Martian helicopters.
Building directly on the incredible, paradigm-shifting success of the Ingenuity helicopter that proved powered flight was possible in the thin Martian atmosphere a few years ago.
Exactly. They are designing a fleet of these advanced autonomous helicopters to fly ahead of the rovers, scout the Martian surface, map the terrain in high definition, and find the safest, most resource-rich candidate landing regions for future human missions.
You're looking ahead.
So even as they are pouring $20 billion into laying down lunar infrastructure, their eyes are already mapping out the valleys and plains of Mars.
If we synthesize everything we have dissected from these sources today, what's fascinating is that we are witnessing a fundamental historic pivot in how humanity interacts with the cosmos.
We really are.
We are looking at the messy, politically fraught, incredibly complex, but awe-inspiring transition from merely visiting space to actually permanently living in space.
And it hasn't been smooth.
You know, the agonizing delays of Artemis III, the thermal physics of heat shields, the political fallout from the death of the multi-billion-dollar Lunar Gateway. None of these were dead ends. They were the necessary, painful catalysts that forced the birth of Project Ignition.
They were wake-up calls.
They forced the realization that if we want a permanent human foothold in the solar system, we have to bypass the slow orbital toll booths. We have to go direct to the surface. We have to build an assembly line economy of scale. And we have to harness the power of the atom to survive the dark.
Which leaves you, the listener, with one final, lingering question to ponder as we wrap up this deep dive.
That's a big one.
We are talking about a $20 billion Project Ignition that relies overwhelmingly on private commercial companies to build the landers, the habitats, and the rovers. We have a billionaire tech entrepreneur administrator driving the timeline. We have global corporate supply chains stepping in where international space agencies were pushed out. If commercial entities own the rockets that get us there, own the habitats we sleep in, and own the nuclear power stations that keep us from freezing, who ultimately owns the infrastructure of this new frontier?
That's the $20 billion question.
Are we building a unified public human outpost for all mankind, or are we quietly laying the foundation for the first privatized corporate company town in space?
Something to think about.
Something to chew on for sure. Thanks for joining us for this deep dive. Keep questioning the world and the world beyond.